Hi everyone. So continuing our previous lecture, in this lecture we are going to study about N-channel enhancement type MOSFET. Previously we studied about depletion type MOSFET. So now what is the major difference between enhancement and depletion type MOSFET? In depletion type MOSFET, the channel was already present. Here there is no channel. There is no channel. In depletion type of MOSFET, there was this N channel present. But now there is no channel. So no initial channel. No initial channel. So here you will have to frame the channel by your own by applying some gate potential. No initial channel. So if my gate potential is 0, no matter whatever you applied at the drain, what we will do, we will always keep source as a reference and source and body will always be shorted. Now if my VGS is 0, no matter whatever you apply at VDS, there will be no current, right? If my gate is 0, no matter whatever you apply at the gate, there will be no current. Let's see the condition one by one. Let's take the first condition when VGS and VDS both are 0. Both are 0, absolutely nothing is there. So certainly there will be 0 ampere current, no current is there. VGS is 0 and VDS is negative. Here you are applying negative potential. Negative potential. This is the scene here, right? N and P. You are applying negative potential. You are making it forward bias. The depletion width is small. The electric field is less. You are applying negative potential here. The electric field is less. The depletion width is low. The electric field is less. And here, what is happening? Here, this P-type substrate is there. This is P-type substrate. So, what can you expect? That this will be positive and this will be negative. But since you are applying negative potential, there will be very less electric field. The electric field will be in this direction. Now, this can attract the holes. Still, there is very less electric field. Still, we are thinking, what if it attracts the hole? If it will attract the hole and will give the motion in this direction. It is not getting out of the drain. The motion will be from drain to source only. So that is irrelevant. That is needless. If you are applying negative potential, there is no meaning that you will get some current. So we can't apply negative potential. At least we will have to apply positive potential. At least we will have to apply positive potential. So at the negative potential, you will have 0 current. This will be 0 current. Now still my VGS is 0. I am applying positive potential now. So if I am applying positive potential, what will happen? This will be reverse bias. So because of that, there will be high electric field. But whom will this high electric field attract? Are there any electrons? If there was any electrons, they would have gone here. Now these electrons cannot be attracted by this electric field. Why so? Why so? Because there is no channel. Even if this electron is attracted by this electric field, what will happen? In the channel, what is there? In the channel, there is this P-type substrate. So even if this electron is attracted, what will happen? This will be recombining with this hole. So there is no chance that they will be reaching towards the drain and current will flow. So even if you have applied positive drain voltage, still there is no current. Because the gate potential is 0. You have to frame the channel. That's the main task. How will you frame the channel? Now that is the problem. So tell me, what potential you will apply to frame the channel? Positive gate potential or negative gate potential? What do you think? I should apply positive gate potential or negative gate potential? Take your time and think about it. I should apply positive gate potential. Why so? Because if I apply positive gate potential, what will happen? There will be negative node here. If I am applying positive here, positive to gate, so there will be negative node here. So this will supply electrons. This will supply electrons here. And some of the electrons will reach here. Some of the electrons may reach here. Some of the electrons will recombine with these holes, and then if you keep on increasing the VG potential, what will happen? Some of the electrons will reach here and then it will frame the N channel and then the current can flow. So we have to apply positive potential. At least this thing we got to know. If you apply negative potential, it will not work. So we have to apply at least positive potential. So here also the current will be 0. Now what I am doing, I will apply some positive potential at the gate. So here I am applying some positive potential and drain is also at positive. But the positive potential that I have applied, that is very less. That is very less, not much. So what will happen? This is the positive potential I am applying. This is the negative potential. So electrons are being supplied. Electrons are being supplied here. Right? And here what is there? This is the condition here. Also the same condition is here. Now electrons are reaching there, and there some electrons are recombining with these holes, and some electrons are recombining with these holes. So you have to keep on increasing the Vg value. You have to keep on increasing the Vg value. More Vg value means more electrons. So now more electrons will recombine with the holes. So when they recombine with the holes, what will happen? Look, Vg is positive. That means electrons will come into substrate. They come into substrate, and what they do? They recombine with the holes. Now my Vg is that enough that these electrons, no, what I shouldn't say these electrons, these holes have been recombined. So in the channel, what do you have? I'm saying that in the P substrate, these holes are recombined. These holes have been recombined. These holes have been recombined. So what you will have? You will have this. Now will there be any current? Can you say these are electrons? Will they conduct any current? No, they will not conduct any current. Why so? Because they are mobile ions. What they are? They are mobile ions. Mobile ions which cannot conduct current. Cannot conduct. Cannot conduct current. So my Vg value is such that these holes have been recombined. But still they cannot conduct current. To conduct the current, you have to apply more Vg potential. So still Id is 0. That means I have to increase Vg potential. I have to increase Vg potential. At some positive potential of Vg. At some positive potential of Vg, the channel will be framed. The channel will be framed. What do I mean by that? Now what is happening? These holes have already been recombined, right? These holes have been recombined. Now further more electrons will be coming now. More electrons will be coming. More electrons will be coming here. More electrons will be coming here. Now these electrons will go and stabilize here. Are you understanding this point? Now they don't. Now these electrons have no work. They are not going to recombine with the holes. Those holes have been recombined. Now these electrons can go and stay here. It's not exactly over this. Okay, just anywhere they can be. Anywhere they can be. They can be here. They can be here. They can be here. They can be here. And this frames the N channel. Because what is N channel? If you forget about this mobile ion, in the N channel there is these electrons. So this will frame the N channel. And our substrate was P. Our given substrate was P. But in this P substrate, we have made the N channel. That means we have inverted the P substrate. In P substrate, we have made the N channel. So we have inverted the P substrate. So that's why it is known as inversion layer. Are you getting this point? So more and more electrons are supplied, and because of that, what is happening? A channel will be framed that will have electrons. This channel will have electrons, and this layer is known as inversion layer. Why it is known as inversion layer? Because in P channel, in P substrate, I should say, in P substrate, we have framed N channel. So we have inverted the P substrate. So that's why it is known as inversion layer. So now at some positive potential of Vg, the channel is framed and the current flows. And now since the channel is present now, since the channel is present or present, since the channel is present now, so the current ID flows. Now the current ID will be finite. Okay, so how the current will flow? The same thing, because at drain side you are having positive potential, that means you are having high reverse bias. If there is high reverse bias, that means there is high depletion region. If there is high depletion region, that means they will attract the electrons. If they will attract the electrons, they will attract the electrons in this direction. That means what will be the direction of current? The direction of current will be this. So the current will flow from drain to source. This I don't need to write, that depletion region, attraction, that we have already studied in depletion type of MOSFET. So the same phenomena is happening here. So the current flows, the direction of current is from drain to source. From drain to source. Just one thing, always keep on revising this device physics, whether it is basic semiconductor physics or MOS physics or BJT physics. Always keep on revising the device physics, otherwise you will forget it. Even the teachers have to revisit the concept when they are going to teach. Device physics is something which can be very forgettable. Okay, it's something very forgettable. It's like Gautam Gambhir. Okay, forget it. So direction of current is from drain to source, because the direction of charge carriers, which are electron, are moving from source to drain. Charge carriers are moving from source to drain, so the current will be from drain to source. Current will be from drain to source. Now at some positive potential of Vg, so at some positive potential of Vg, this thing is happening. So the potential, so the gate potential at which the current flows, that potential is known as threshold voltage. Did you understand it? At some positive potential of Vg that is happening, so the value of VGS, at which the current flows is known as threshold voltage. So that potential is known as threshold voltage. Threshold voltage, which we show by Vt. This is not thermal voltage. This is threshold voltage. This is shown by Vt. This threshold voltage. Well and good. So now, if my VDS is positive and if I apply VGS greater than Vt, if I am applying VGS greater than Vt, that means now the current will flow. ID flows. How it flows? Because VDS is positive, that means, and VGS is greater than Vt, that means here the channel is framed. The channel is framed, and secondly, Vd is positive, that means there is this high electric field. There is high electric field. This is the high electric field. So because of this high electric field, these electrons will travel. I should use different color of pen. These electrons will travel in this direction, in the opposite direction, and will get out of the drain, and the current will flow. Well and good. Electrons will travel in this direction, will get out of the drain, and the current will flow. The current flows. This is the same phenomena as the depletion type of MOSFET. Our target was to frame the channel, and how it is framed? By applying the positive potential at gate. And this we are studying for what? N-channel enhancement type of MOSFET, and the other name of this MOSFET is NMOS. You call it NMOS as well. By N you would get to know that it is N-channel. So substrate will be of P, the channel is N, that means we will frame the channel N. So in NMOS you need to apply Vg to be positive and drain also to be positive. Both you need to be positive. So in NMOS you need both drain and source to be positive. So this is the first condition where the current flows. This is the condition where the current flows. So ID flows from drain to source. So in NMOS, the current flows from drain to source. And these are shorted only. Both are grounded. Well and good. Now what do we need to see? We will see that after VTH, if I am increasing VGS, what will happen? If I increase VGS, what should happen? If I increase VGS, that means more and more electrons will be coming here. VGS is positive. So from here, negative side of battery, electrons are coming. So more and more electrons will come. That means in the channel we will have more charge carriers. Electrons will increase. In the channel, electrons will increase. That means if more electrons are there, that means there is more current. So if we are increasing VGS, there will be more electrons in the channel. And if there are more electrons, that means there will be more current. So ID will increase. So until VT was some positive potential. So till this point, there was no current. And then suddenly the current rises. And the current rises in a square law manner. Why it is square law? No one will ask you. The current rises in square law manner. Why it is square law? We have to derive it. And no one is going to ask you the derivation. Intuitively, you can't tell why it increases in square law manner. We have to derive it with taking some approximation and all. So we will just see the relation. We will just see the expression. What is the expression? So it increases like this. Well and good. Not necessarily it will be square law. It depends on the region, linear region and saturation region, that we will see. So till this time there was no current. So this region is known as cutoff region. Cutoff. Why it is cutoff? Because there is no current. And this curve is very, very important. Well and good. Now condition 6 is, now my VGS is greater than VT, which is fixed. That means I have given enough gate voltage to conduct the current. Now my VDS is also positive, but VDS is increasing. That means I am increasing my VDS voltage. So I guess I can simply copy this one. I am increasing my drain voltage. So what will happen? If I increase my drain voltage, initially the current will increase, but later on it will saturate. The same thing that we studied in depletion type of MOSFET. What will happen? If VDS is increasing, then depletion width increases. Instead of that, I should directly write electric field. E field will increase. If E field increases, that means electron gets more force. If electron gets more force, that means there will be more current. But at some value of VDS, what happens? At some value of VDS, let's draw the channel. So at some value of VDS, what happens? The channel is getting depleted of charge carriers. Although the electric field is strong. This is N channel, no? Yeah. Although the electric field is strong here. Okay, I don't need to make the plus minus ions. If I am increasing VDS, what is happening? The channel is getting depleted of charge carriers. So from here to here, VDS is increasing. You go from down to up, your VDS is increasing. So if VDS is increasing in the channel, this is the channel, the channel is getting depleted of charge carriers. Initially this much of charge carriers were there, but slowly the channel is getting depleted of charge carriers. Although there is strong electrical field, but still the charge carriers are less, so the current will saturate. At some value of VDS, I will directly write the current will saturate, because you know the region. What is the region? At some value of VDS, the current will saturate. Why it will saturate? You know the region. The current will saturate. So initially it increases linearly, then at some point it saturates. After that it saturates. So yeah, I forgot to tell one thing. This region. So here it is saturating now. Here. So this region is known as linear region. This is linear region, because here the current is increasing linearly, and the further region is known as saturation region. Here the current is saturated. So in the previous graphs as well, where we drew it, in these graphs as well, you can show that these are linear region and this is saturation region. This is the enhancement type graph. Okay, these are the previous graphs where I forgot to write. And one more thing, in depletion type region, this mode is known as enhancement mode and this mode is known as depletion mode, because here the current is decreasing, and if VGS is high, their current is increasing. This is not important, no one will ask you about it, but still just for information, this mode is known as enhancement mode and this mode is known as depletion mode. This is for depletion type of MOSFET, which I forgot to write in the previous lecture. Yeah, so where we were, so here we have drawn the characteristics, right? Now we can draw the final characteristics which I have already drawn. Now you need to tell me the relation between VDS3, VDS2 and VDS1. Tell me which one will be the highest one. At a particular VGS, in one curve you are getting highest current, in one curve you are getting medium current, and in one curve you are getting lesser current. That means in one of the MOSFET, in one of the condition VDS3, in this condition there is the maximum current. That means here the drain voltage is at highest. Drain voltage is positive, very positive. It is very positive. So it is very positive. So there will be high electric field. If there is high electric field, that means it can sweep up more electrons. If it can sweep away more electrons, that means there will be more current. So VDS3 is higher than VDS2 is higher than VDS1. You don't need to mug it up. You need to understand the logic. What is the logic? Tell me what will be the logic here. Which will be higher, VGS3 or VGS2 or VGS1? Here your VDS is same. VDS is the same. VDS is constant. Now you are increasing the VGS value. If you increase the VGS value, what will happen? If VDS is same, if you are increasing VGS value, that means you are increasing positive potential at gate. If you are increasing positive potential at gate, that means electrons will be supplied. If electrons is supplied, that means in the channel you will have more electrons. If you are having more electrons, that means more current. So if you increase positive potential at gate, that means the current will increase. So here, which is the maximum current? This is the maximum current. That means this VGS is the maximum. So VGS3 is greater than VGS2 is greater than VGS1. Are you able to connect? If you are listening to me with your full concentration, then only you will be able to understand. You should have full concentration here. What did I say? More VGS, that means more current. More VGS, that means higher positive voltage, that means more electrons are supplied. If more electrons are supplied, that means in the channel we are having more electrons, so more current. So more VGS, that means more current. More VDS, that means more current. So VDS3 is higher than VDS2, higher than VDS1, and here this is the relation. So this was our N-channel enhancement type MOSFET. So what did we do here? If here VGS is 0, if there is no VGS, we are not having any current. So we have to give some threshold voltage. We have to apply some minimum voltage to get the current, right? So this can work as an amplifier. Now my current is depending on my VGS voltage. At that time, although my current was depending on VGS voltage, but even if I haven't applied any VGS, still I was getting some current. So that is undesirable, right? Now we are getting a desirable thing, that is, if there is no VGS, the current is zero. So for the current to flow, VGS should be greater than VT. For the current to flow, VGS should be greater than VT and VDS should be positive. Now, here the current saturates in this region. The current saturates. So at what potential of VDS the current saturates? This potential is known as VD set. Here the current is saturating, right? VD set. So what is that potential? That potential is applied VGS. This curve is there for some particular VGS value, right? Applied VGS minus VT. This curve is there for a particular VGS value, right? So for this curve, what will be the threshold voltage? Tell me, for this curve. For this blue curve, what will be the threshold? What will be the saturation voltage? Not threshold voltage. What will be the saturation voltage? For this blue curve, the saturation voltage would be VDS1. I can write, what would be my VDS1? That VDS1 would be saturation voltage. I am writing saturation voltages. So that would be VGS1 minus VT. So that would be the saturation voltage. What will be the saturation voltage for the second curve? VDS2. That would be VGS2 minus VT. And what will be the saturation voltage for the third curve? That would be VGS3 minus VT. So this particular expression is important. What is the saturation voltage? When the current saturates, but what is the value of that? That is VGS minus VT. So if your VDS value is higher than VGS minus VT, that means your current will saturate. If your VDS value is lesser than VGS minus VT, that means you are working in linear region. Are you getting this point? Here, if I write your VDS is, where should I write? Here I can write. If your VDS is higher than VGS minus VT, that means you are in saturation region. The current is saturated. And if your VDS is lower than VGS minus VT, but it should be at least greater than 0. VDS has to be greater than 0 always. Should be greater than 0. Then if VDS is less than 0, that means it is in cutoff. If VDS is less than 0, that means it is in cutoff. If VDS is less than 0, that means there will be no current. Here there will be no current. If VDS is less than 0, that means this will be cut off. So if VDS is less than 0, it will be cut off. If VDS is less than VGS minus VT, it will be in linear. And if VDS is greater than VGS minus VT, that means it will be in saturation region. Well and good. So now we will see the MOSFET current equation. Okay. So what this I have drawn, this is the channel. This is the channel. Channel I have drawn. But channel in 3D. In 3D. Till now we were watching the channel something like this. This is how we were watching the channel. But now we are seeing it in 3D. So this will be my channel. So this particular thing. So here I will not write channel. I will just show it that this is my channel. So now this particular length is known as L. This is the channel length, and this behind this one, this is known as width. So here it is difficult to show, but I will show it somehow. This is my width. In this diagram it is more clearer. Length and width. Got it? So what will be the current equation in linear region? What is the linear region? When VDS is lesser than VGS minus VT. You will remember the graph. Okay, VDS is lesser than VGS minus VT. That means that is the linear region. Now I will write the expression of current. From where the formula came, no one will ask you the derivation. So just the simple formula, that is mu n cox W by L VGS minus VT into VDS minus VDS square by 2. This formula you will have to remember, but you will use it so much of time that you will always remember it. Now what is mu n here? That is mobility of electrons. Mobility of electrons. WL you know, right? L is channel length, and W is channel width. Now what is this COX? So let's see it. At the upper side what you are having, this is the channel. Above channel what you are having? Above channel you are having oxide layer, right? Look, this is my channel. Below it there is channel, right? Above it what you are having? Oxide. Above oxide what you are having? Metal. Metal, oxide, and after that you are having your channel, or you can say semiconductor. After that you are having your semiconductor. Metal, oxide and semiconductor. Now if you are giving some supply here, some positive supply, let's assume. So because of that there was electrons coming, so basically negative supply was coming here, right? If we are giving positive supply here, so because of that negative supply was coming. So isn't it acting like a two plate of capacitor? Isn't it acting like two plates of capacitor? Two plates of capacitor are there, and in between there is some oxide. So it will give rise to some capacitance. What is the formula of capacitance? That is epsilon by width. This width is TOX. This width of the oxide, that is TOX. And epsilon is simply permittivity. This is TOX and this is permittivity of the this is oxide layer. What is oxide layer? SiO2. We will talk about it, why oxide layer is used, what is the use of oxide layer, we will talk about it. So permittivity. This is permittivity of oxide layer. And then TOX is the length, right? And metal, oxide, semiconductor. So COX is this. So this you need to know. Okay, this is COX. So WIL we know, mu n we know, VGS we know, applied VGS, VT we know. What is VT? Threshold voltage. And instead of VT we should write VTN, threshold voltage of NMOS. So VTN, threshold voltage of NMOS. Threshold voltage. Okay, one more interesting thing we will see here, that in the NMOS, what is the scene? The drain is at positive potential. The drain is at positive potential and source is at lower potential. So the drain is at higher potential and source is at lower potential. In case of NMOS, drain is positive and source is negative. Source is zero actually, because we are taking that as a reference. So drain is positive, that means drain is at higher potential. So in case of NMOS, the potential which is at higher potential, the node which is at higher potential, that is known as drain, and the node which is at lower potential, that is known as source. Now I will tell you one interesting thing. Just see the structure of a MOS. Just see this structure. Isn't it symmetrical? Isn't it symmetrical about this? Like if it is in front of you and you don't know what is source, what is drain, so how will you decide what is source and what is drain? Because it is symmetrical only, no? If someone is seeing from this side, he will say this is drain and this is source. If someone is seeing from this side, he can say this is drain, this is source, because this is symmetrical. But in case of NMOS, what did we find? If there is a substrate given to me, I will see that is P substrate. So it has to be NMOS. And in NMOS, drain is at higher potential. So I will check the potential of these two nodes. So the node which is having higher potential, I will call that as drain, and which is having lower potential, that will be my source. And gate will be surely the controlling one, it will be in between. So the confusion will be between drain and source, because the structure is symmetrical. So in case of NMOS, the node which is at higher potential, that is drain, and the node which is at lower potential, that is source. Are you getting this point? In case of NMOS, the node which is at higher potential, that is drain, and the node which is at lower potential, that is source. So we have written the current expression for linear region. We have to write the current expression for saturation region as well, that we will write. But before that, let's write a note. What is the note? In case of NMOS, higher potential node is drain, and lower potential node is source. And what is the direction of current flow? The electrons were going from source to drain. That means the direction of current flow is from drain to source. And current flow is from drain to source. From drain to source. That means from higher potential node to lower potential node. Here I did not write opposite, right? ID flows from drain to source. I did not write from drain to source. Okay. So the electrons are going from source to drain. So the direction of current will be drain to source. And which was at higher potential? The drain was at higher potential. Drain was at higher potential and source was at lower potential. So if I am given a MOS, first I will identify if it is NMOS or PMOS. I identified it is NMOS. So if it is NMOS, that means the one which is at higher potential, that will be drain, the lower potential will be source. So I will also know the direction of current, that it will flow from high potential node to low potential node, from drain to source. Are you getting this point? Now I will write the current in the saturation region. So for the saturation region, tell me one thing. Whatever the current is here, the same current will be here, right? The current is constant. So what current will be there at this region? At this region. What did we say? That previously it was following the linear manner. This manner it was following. Previously it was following the linear manner. This manner it was following. Suddenly it has changed. Suddenly it is saturated. So if I put in case of VDS, if I put VGS minus VT, that will give me saturation current, because this node is VDS minus VT, right? This node is VDS minus VT. This node is VDS minus VT. So if I put VDS minus VT in that linear current expression, if in this expression, in case of VDS, if I put VGS minus VT, I will get my saturation current. Are you able to understand? Because at if I put VDS equals to VGS minus VT, I will get the current here. Now the same current is the saturation current. The same current is the saturation current. So if in the expression, in place of VDS, I am putting VGS minus VT. So if I put VGS minus VT here, what will be happening? It will be VGS minus VT square. It will be VGS minus VT square. This will be VGS minus VT square, because in place of VDS, I am putting VGS minus VT. And this will be, in place of VDS, you are putting VGS minus VT square. And by 2. So this complete expression will be made VGS minus VT whole square by 2. So what will be your formula? Mu n Cux W by 12 VGS minus VT square. The formula will become mu n Cux W by 12 VGS minus VT square. So this is also very important. In the end, I will give you a conclusion that what you all need to remember from all this lecture, from the complete lecture, what you all need to remember for analog electronics, that I will give you the conclusion in the end of this part. That means in the end of the next video, I will give you the conclusion. So for now, we are writing the important points. So what is the point? I am just putting in place of VDS, I am putting VGS minus VT. So what I will get? यार ये बार बार टेढ़ा हो जाता है यहाँ पे ये राइटिंग पैड. Mu n Cux W by 12 VGS minus VT, VTN we can write VTN square. So that will be my current in saturation region, right, which is constant. Understood? Well and good. So is there anything do I need to write? Or is that it? That's it, right? MOSFET is a symmetrical structure. So till now what we have studied the working of NMOS. So what is the working of NMOS? You have to apply some positive potential at drain and also some positive potential at gate, but that small potential is not enough. You have to apply higher than a particular potential so that the channel is framed. If the channel is framed, then positive potential at the drain will attract the electrons and the current will flow. So to frame the channel, you have to apply a positive potential at gate, and when it is framed, the current will flow. Now the current is flowing and electrons are moving from source to drain. That means the current will be from drain to source. Now which will be drain, which will be source? The one which is at higher potential, that will be drain, and one which is at lower potential, that will be source in case of NMOS. So this we saw in case of NMOS. Now we are going to analyze PMOS. PMOS means P channel enhancement type MOSFET. So this you can analyze on your own, right? You can analyze on your own. So try making the transfer characteristics, ID versus VGS curve and ID versus VDS curve by your own, and then recheck if you are making it clearly or not. So tell me, what potential you should apply here? Negative or positive? Or positive? Which potential you should apply? Negative. Why so? Because if you apply negative, then only depletion region will be found, because this will go into reverse bias when you apply negative potential. So you have to apply negative potential. And at gate, what you need to apply? Negative or positive? Or positive? You need to apply negative, because if you apply negative, what will happen? If you apply negative, then from here holes will be supplied. If holes are supplied, they will reach here, and that will frame the channel. So negative potential here and negative potential at the drain. So here the channel is framed, and now this drain will attract the holes and the current will flow. So what will be the direction of current? The direction of current will be from source to drain, because holes are moving from source to drain. If the holes are moving from source to drain, so the direction of current will be from source to drain. Now drain is at a negative potential. Drain is at negative potential and source is grounded. So which one is higher potential? Drain is negative and source is grounded. Which one is higher? Source is higher. So in case of PMOS, higher potential is source and lower potential is drain. So this is all we need to see, and we will make the transfer characteristics. Also write down the current equation, which will be same as NMOS only. So tell me, what will be the current here? Both 0, 0 current. VGS is 0, still the current will be 0, because no channel will be framed. Here what will be the current? VGS is 0, whatever you apply, the current will still be 0. Here what will be? VGS you have applied negative, but still very less. That means channel is not framed. Channel is not framed. You have to apply more negative potential. You have to apply more negative potential. You need to apply more negative potential. If you are applying more negative potential, what will happen? The channel will start framing. Channel will start framing and the current will flow. So basically, let's assume that first I am applying -1, then I have to apply -2, and let's assume if VG is -3, my current flows. So what I will write, that my VGS value should be lesser than VT for the current to flow. This is my VT, because here the current flows. This I can call VTP. So for lesser value than this, if VG is -4, if VG is -5, the current will flow. So I will write that my VGS should be lesser than VTP. At that point my current will flow, because gate potential is negative. Are you getting this point? What will be my VTP? VTP will be my -3. Now gate potential is negative, source is at grounded. This is grounded. This is also grounded. Source is at grounded and this is also grounded. Now I am applying negative potential. That means I will apply VG to be -4 or -5. So I am decreasing the potential. So if my VGS is lesser than VT, that means if my VGS is less than -3, it can be -4, it can be -5, it can be -6. So if my VGS is less than -3, that means my current can flow. Are you able to understand this point? Say yes or no. So when VGS is less than VTP, the current will flow. So like that I can make a line so that you will be able to understand it. So this I will say -1, -2, -3, you are applying Vg in this direction. Vg you are keep on decreasing. Vg, let's assume this is your VTP. So if my VGS is less than VTP, then my current flows. First thing is that you have to apply negative potential at gate, but also the negative potential should be so less that it should cross the VT value, and then only the current will flow. And if drain is negative, that means what is happening? It is framing the depletion region. It is framing the depletion region. That means it is giving you a high electric field that can attract the holes. I hope you are able to connect now. So when VGS is less than VTP, then your channel will be framed. This will be your channel where holes will be there. This is your channel. Now there is a chances that current can flow. So okay, before moving on to the next condition, I will tell you one important thing, that is this, that now you have to remember two conditions. No, in case of NMOS you will have to remember that VGS is greater than VTN. Sorry, in case of NMOS, let's move on to the next page. So in case of NMOS you will have to remember that VGS is greater than VTN. This is in case of NMOS. Then in case of PMOS you will have to remember that VGS is less than VTP, and this is also negative, and this potential is also negative. So it will create confusion, right? So what is the simplest way to remember that this is you are remembering? So what you will do in case of from NMOS to PMOS, if you are going, what you will do, you will just interchange gate and source. So what you will write, that your VSG should be greater than mod of VTP. I am saying that my VGS is -4, my VTP is -3, and my VGS is -4. This I am talking about PMOS. VTP is -3 and VGS is -4. That means here I am. That means my current will flow, right? Current will flow. ID will flow. If my VGS is -4, what I can write? My VSG is 4. So if my VSG is greater than mod of VTP, then my current flows. That means 4 is greater than 3. So my current will flow. What I can write, that my VGS is less than VTP. This I can write if I am not using mode. But if I am using mode, so I can write my VSG is greater than VTP. So in the examination, you are not going to think that much. What you are going to remember? You are going to remember only NMOS. You are going to remember only NMOS part. So in the NMOS part, you have remembered 3 things. What are those things? First thing is that your VGS should be greater than VT for the current to flow. Your VGS should be greater than VT for the current to flow. So for PMOS, if you need to write VTN, so for PMOS, if you are writing, what you will do, VGS would be replaced with VSG should be greater than mod of VTP. These signs will not change. Greater than, lesser than. These signs will not change. These sign will remain as it is. Mod of VTP. What is the other thing you remember? Saturation voltage. What is the saturation voltage? VD sat was that if your VDS is less than VGS minus VT, if your VDS is less than VGS minus VT, you are working in linear region, right? If your VDS is less than VGS minus VT, you are working in linear region. That is for NMOS. So what will be the case for PMOS? VDS VSD is less than VSG minus VTP. So basically, you are replacing your VGS with VSG, you are replacing your VDS with VSD, and you are replacing your VT and with mode of VTP. That's it. No sign of arrow and all these will change. Because if these keep on changing, you will be confused. So this is just my shortcut, or this is how I solve the problem, that I remember for NMOS. I just remember the graph. Okay, VDS is greater than VGS minus VT, I will be moving to saturation region. VDS is less than VGS minus VT, I am in linear region. If VGS is greater than VT, that means I have cleared the cutoff. Now my current can flow. So these things I remember. Now for writing for PMOS, I just have to interchange the source to gate, source gate and source drain. So what will be my condition for PMOS? To overcome cutoff, what should be the condition? That my VSG should be greater than mod of VTP. Now for saturation, what will be the condition that for linear region my VDS should be less than VGS minus VT. That means my VSD should be less than VSG minus mode of VTP. And what should be the condition for saturation region? The saturation region condition would be my VSD should be greater than VSG minus mode of VTP. That's it. No sign of arrow, only one sign of arrow I am remembering, and then I keep on interchanging. Are you getting this point? So by that we can solve the problems more quickly rather than thinking all that. So when we are doing the circuit analysis, we can't think that much, right? But if the question is on EDC, you can think that much. But if you are doing the circuit analysis, you don't need to think that much. So from going from NMOS to PMOS, VGS should be replaced with VSG, VDS should be replaced with VSD, and VTN should be replaced with VTP. So what was the cutoff region in NMOS? That was your VGS should be less than VTN. That was the region. So here it will be VSG should be less than mode of VTP. That is the cutoff. What will be the on region? That your VGS should be greater than VTN. Here what it will be? VSG should be greater than mode of VTP. Once you start solving the problems, it will be very easy for you. What was the condition for linear region? That your VDS should be less than VGS minus VTN. What will be the condition for linear region here? Your VSD should be less than VSG minus mode of VTP. What will be the condition for saturation region here? What was the condition? Your VDS should be greater than VGS minus VT. Here VSD should be greater than VSG minus VT. In case of NMOS, which was at higher potential? Drain. So here we are always writing drain first and source later on. And in case of PMOS, which is at higher potential? Drain is at negative and source is at ground. So source is at higher potential. That's why we are always writing source first. Are you getting this point? So one which is at higher potential, that we are writing initially. So these things you need to keep in mind. This is the this is all you need to keep in mind. After that you can write down the current equation and everything. Now we are left with one condition, that is this, that my VGS is less than VT and my VDS is negative. So what will happen? I can write this, or what I can write, or what I can write, that my VSG is greater than mode of VTP. VGS is less than VTP. That means here I am applying more negative potential. That means my VSG is greater than mode of VTP. This I can write. And here I am writing that my VDS is negative. VDS is negative. That means here I am applying negative potential. If I am applying negative potential here, so what I can write? Negative here and grounded here. This is grounded. This is grounded. And at drain I am applying negative potential. So what I can write? My VSD is positive. So what will happen? ID flows. Tell me the direction of ID. What will be the direction of ID? Holes are moving from source to drain. So the ID direction will be source to drain only. Source to drain. In the direction of movement of holes, that will be the direction of ID only. So holes are moving from source to drain, so ID current will also move from source to drain. Now we will draw the transfer characteristics. So ID versus VGS we are drawing. ID versus VGS, not VSG. ID versus VGS, right? The current direction it is asking, that is from source to drain. Source to drain. ID versus VGS. VGS, that means source is grounded, VG potential. VG potential you have to apply negative. So till a particular negative voltage, you are not getting any current. Till a particular negative voltage, you are not getting any current. After this negative potential, you will get some current. Right? Now let's do the same for VSG. ID versus VSG curve. Now your source is at ground, but gate is negative. Basically, what is the condition? That your VSG should be greater than mode of VTP for the current to flow. So this is your VTP. Here you don't need to think, right? This is mode of VTP I will write. Because for PMOS, threshold voltage is negative and for NMOS threshold voltage is positive. And this is how it will go, right? Condition 6, ये कौन सी condition है? अच्छा, now if we keep on increasing VDS, what will happen? Negative supply is increasing. If I am increasing negative supply, basically here I am increasing the, this was my NMOS, so here I am increasing the negative supply. What will happen? The reverse bias here will increase, so the current will increase. So if I am increasing VDS in negative direction, that means if I am increasing negative supply, what will happen? The reverse bias will increase. If the reverse bias increasing, depletion region will increase, more electric field, more current, right? But at a particular VDS value, the current will saturate. Why it will saturate? Because in that channel we are having less charge carriers now. There will be less poles. Although the electric field is very high, but still there are less poles, so the current will saturate. So just the final answer we will write. What is that? Current initially increases linearly and then saturates. So ID versus VDS you are drawing. That means the drain is at negative potential. So for negative graph you will draw. At first it is increases and then it saturates. Increases and then saturates. And ID versus VSD if you are drawing, what will be this potential? Tell me. That will be VGS minus mode of VTP. Because VGS is also negative. Source is 0, VG is negative. So negative, no, not mode of VTP. It should be mode of VTP or only VTP. बताओ भाई, mode of VTP or only VTP? VSG minus VTP. VSG is already higher. Yeah, it should be directly VTP, not mode of VTP. VSG minus VTP. But now we are writing VSD. So here you don't need to think. What you know? What will be my VSD set? VSD set. That will be VSG minus mode of VTP. That's it. Look, you have to think something like if I keep on telling, you will not be able to understand everything. I have given the enough concept. I have given you enough tricks to remember the things. Now it's up to you how much can you think. I told you one simple thing that you remember for NMOS. If you are writing for PMOS, just interchange VDS with VSD, VGS with VSG. The arrow sign will remain the same. Look, the graph is also same. This graph is also same now. There is no change in the graph. That's why people call EDC complex, but these things are necessary for understanding MOSFET circuits. And also for interview, it is very, very important. So this is VSG minus mode of VTP. And this current is ID set, we already know. So this much of region is linear and this is saturation. Now you are able to connect the dot. So now we will see the final characteristics that I have drawn. I need the relation between VSD1, VSD2, VSD3. So these curves we will remember. We will remember by this, not these curves. These curves we draw now. These one we are not going to remember. These curves we are not going to remember. We are going to remember in the positive direction only. So here VSG is there, here VSD is there. So tell me which one is higher? VSD1 is higher, VSD2 is higher, or VSD3 is higher? VSD1 is higher than VSD2 is higher than VSD3. If I am saying VSD is higher, VSD is higher, VSD is higher, that means drain is more negative. If drain is more negative, that means more reverse bias, more depletion region, more current. So VSD is higher, that means drain is more negative. And if I am applying more negative, that means more current will be there. So VSD is higher. Here tell me what is higher. VSG1 is higher than VSG2 is higher than VSG3. If I am saying VSG is higher, that means this gate is more negative. This gate is more negative. If I am saying VSG is higher, that means gate is more negative. If gate is more negative, that means more holes will be supplied. If more holes are supplied, that means in the channel we will have more holes. And if more holes are there, more current will be there. So here we are having more current. So VSG1 is higher than VSG2 is higher than VSG3. Well and good. Let's write down the current equations. So while writing the current equation, what you will do? Same, VGS should be greater than VSG, VDS should be greater than VSD, and VTN should be, sorry, VGS will be replaced with VSG, VDS will be replaced with VSD, and VTN will be replaced with VT. So linear region, what is the condition? Without turning on the pages, you have to write the condition. What is the condition for linear region? That your VSD should be greater than VSG minus mode of VTP. By remembering the which condition? By remembering the condition of NMOS, I can directly write the PMOS condition. So what will be my ID? My ID will be mu n COX W by L VSG minus VT into VSD minus VSD square by 2. Very easily, wait. VSG minus mode of VT I will write here. VSG minus mode of VTP into VSD minus VSD square by 2. What will be my saturation region? That will be VSD is, oh sorry. This should be lesser. Sorry for that. Big error from my side. People would have got confused and wasted their time there. VSD is lesser than VSG minus VTP. Here VSD is greater than VSG minus VTP. What will be my current? Here one more error is there. I am really sorry. It should be mu P COX W by 2L VSG minus VT, VSG minus mode of VTP whole square. Are you able to do it? Okay, we will take up an example so that you don't get confused. We can take up an example to find the current. Okay, to find the current and all. Yeah, one note I will write. What is that note? In PMOS, higher potential is, what is higher potential? Source, because drain is negative. In case of PMOS, higher potential is source and lower potential is drain. And what was the direction of current? Source to drain. We can write the same thing for NMOS as well, although we have already written, but still for comparison we are writing. In NMOS, what was the higher potential? Higher potential was drain. Drain was positive there. Higher potential was drain. If you have remembered the pictures in your mind, it will be very easy. What will be lower potential? Lower potential was source. And what is the direction of current? Direction of current will be drain to source. These things you need to know, direction of current and all those, because electrons are moving from source to drain, so direction of current was drain to source. These things you need to know. You need to know these equation, you need to know these conditions. Okay, so this note is very important. These two equations are very important. These two curves are very important. and then these conditions are very important. Cutoff on linear saturation, these conditions are very important. Then coming to this equation, very important, the equation, and for this curve are very important. So in these 2 hours whatever we have studied, 2.5 hours whatever it takes, so these things are important in that will be used for circuit analysis. But you should be conceptually sound, that how current is coming, what is the region of current coming, which potential I should apply. In case of PMOS, drain and source should be positive. Okay, so these things you should know. Okay, and one more thing is left that I did not write, why we use enhancement type of MOSFET for amplification. So in enhancement type of MOSFET, what is happening? For zero potential, there is no current. So your current is depending on the controlling voltage. If there is no controlling voltage, there is no current and no output. Now, if I am increasing my controlling voltage, so after a certain controlling voltage, I can get some output. So enhancement type of MOSFETs are used for amplification. So that I can write in next lecture. In next lecture, we will write the enhancement type MOSFET are used for amplification. The region we will write. Then we will see accusation. One numerical we will see, finding drain current. We can see that. Very simple numerical we will see. And then we will see some important definition, that why oxide is used. These kind of question we will see. Then we will see 2 important concepts, that is known as short channel effect. So that is channel length modulation and body effect. These 2 things we will see, channel length modulation and body effect. So that will conclude our MOS physics. So that is the part which is important for MOS physics. Well and good. I hope you are enjoying the lectures. So okay, let's meet in the next lecture. Thank you.